Welcome back. Today we're talking about vectors. We're going to do day one of vectors today. It tells us here quantities such as force and velocity involve both magnitude and direction and cannot be completely characterized by a single real number. To represent such a quantity, you can use a directed line segment. We call that a vector. Most of you guys learned vectors in physics, and so if you did, then that's great. This is going to be kind of a little bit of a review on just the basics of vectors. That's all we're going to do here in pre-cal is just the basics of vectors. Our directed line segment here, we're going to call PQ, has an initial point at P and a terminal point at Q. So our starting point is going to be P, and our ending point is going to be our Q. And that's an ordered pair. If you remember this from geometry, that line on top there is talking about the line segment, and it's got the arrow part over the Q because we're starting at P and ending at Q. Its magnitude or length, so this is its size basically, the length of that line segment is going to be denoted by these symbols here. It's got two little lines there on each side of our PQ. So we've got two lines and then two lines on this side, and that stands for magnitude. And it is found using the distance formula. The distance formula is going to tell us that length. Two directed line segments that have the same magnitude and direction are equivalent. That means that there could be several vectors that have the same magnitude and direction. Vectors are denoted by lowercase boldface letters such as U, V, W. A lot of the times you're also going to see it with the line on top. That also means vector there, or V, or W. So that little W with the line on top, that also means vector. For the component form of a vector, with an initial point of P as X1 and Y1. There we go. That's just an ordered pair. Remember, ordered pairs are X comma Y. So this is telling us X1 and Y1. And the terminal points or ending point is Q, and it has X2 and Y2. Again, that's just the ordered pair where it's ending at. It's going to be represented like this. This is a bracket, not a parentheses. It looks kind of like a sideways V. So this right here, that's the way we write the component form of a vector. And so what they've done here is they've taken the two X values and subtracted it. So we've taken our final X and subtracted it from our initial X, and taken our final Y and subtracted our initial one. So this gives us our horizontal movement. And this part gives us our vertical movement. So the X2 minus X1 gives us the horizontal, Y2 minus Y1 gives us our vertical. It says find the component form and magnitude of the vector V that has initial point -2, 3 and terminal point -7, 9. So our initial point is -2, 3. So I'm going to graph that. And then our terminal point is -7, 9. And so our vector starts here and ends right here. There is our vector. So now we're going to find its component form and its magnitude. The component form tells us the horizontal and vertical movement, so that direction, and the magnitude tells us the length of that vector. So we'll start with the component form, and I'll go ahead and label that as vector V. So we use our bracket, and then we're going to take our final X and subtract it from our initial one. So we get -7 minus a -2. And then there's a comma. And we're going to do the same thing for our Y's because that's going to find our vertical movement. So 9 minus 3. And so remember, when you have a minus and a negative, those two signs cancel out. So that's -7 plus a 2, which gives us -5. And 9 minus 3, which is 6. There is our component form of the vector. And that gives us our direction. That was algebraic. Geometrically, we can look at this graph and see it. This is -5, so I know it's going to the left. So 1, 2, 3, 4, 5. That's our X movement or horizontal. And then 6, 1, 2, 3, 4, 5, 6 gets us to our endpoint there. That is our vertical or our Y movement. So that's what this is right here. It's giving us that horizontal and vertical for the direction of our vector. For the magnitude, and we represent that with the two little lines, that's going to give us this length of this vector. And we said we can use the distance formula. So if you look at this distance formula, that's x squared minus x1 squared. Well, that's the same thing we had right here in order to find the direction. We took x2 minus x1 squared. So I can just set that up, given this right here, as -5 squared plus 6 squared. Now the math on that part is easy. We've got 25 plus 36, which is the square root of 61. You can find the decimal approximation if you want, or you can leave it as our radical in the exact form. So if asked the magnitude, that's it right there. If asked the direction or the component form, it would be this one here. All right. We're going to take a look at this problem here. It says Sam is pushing a sled. The vector u, where u is equal to 5, -3, models his movement. So remember, this is direction. And so 5 is our x. So we know we're going to go 5 on the horizontal, which would be to the right since it's positive. And -3 is our vertical. So we would go down 3 since it's negative. Which of the following pair of points could be his starting and ending points respectively? So we're going to take all of these and check them. So that first one is 0, 0 is our starting point, and -5, 3. And so our vector is right here. That's A. And so we can check this two ways. We said this would be right 5 and then down 3. Well, from my initial point, right 5 and down 3 would be over here. So we can see that's not happening for the geometric way. If we do it algebraically, then we would use that formula to subtract our y values and our x values. So we get -5 minus 0, comma, 3 minus 0, which is -5, 3. That is not the same thing as what they were asking here as a +5, -3. The positive and the negative show the direction, so you don't want to switch those. For B, we've got 1, 4, and 4, -1. And so there is our vector B. Here we can see that it's gone to the right 1, 2, 3, and then down 5. Again, that does not match what we did here, so we know it's not going to be B. If I do that algebraically, I take 4 minus 1, comma, -1 minus 4, and that gives us 3, -5, which again is not the same thing as this right here. We're going to try C now, and that one is at -2, -3 as our starting point, and then 3, -6. There's our C vector. Geometrically, I can see this goes to the right 5 and down 3, which is matching that. So geometrically, I've already seen that's correct. I'm going to go ahead and show you algebraically so you can see that as well. We take our 3 minus -2, comma, -6 minus a -3. The minus and negative cancel out, so that gives me a 5. And then the minus and negative cancel out here, and that is a -3, which is what we were looking for. Now, that doesn't mean I stop right there. I'm going to check D as well, because remember that we can have more than one vector that has a magnitude and a direction that are the same. So for our D, we go to -4, 6, and 1, 3. And so this one went to the right, 1, 2, 3, 4, 5, and down 1, 2, 3. So it does match our component form there. I can do it algebraically to show you as well. That gives us a 5, and that gives us a -3. And so we've shown that that also works. So both of these have the same direction, which would match our initial problem. So both of these can show Sam pushing the sled. All right. When you're working with vectors, you can have operations just like you do with the other math problems, like adding, subtracting, multiplying. So I'm going to show you how to do that. First algebraically, and then again geometrically. So on this first one, it tells us let u be 1, 2, and vector v be 3, 1. That is the component form of each vector, and we want to find these. So the first one says to add u plus v. And so we want to take our like terms and add them. So 1 and 3 are the ones that work horizontally. So we would add 1 and 3. And then our vertical would be 2 plus 1. So just like with x's and variables, you want to add those like terms. So I've added the horizontals and the vertical. Again, that's easy math. 1 plus 3 is 4, and 2 plus 1 is 3. So our component form here is 4, 3. This would be our new vector. So we added vector u plus vector v to get this new one. That gives us the component form 4, 3. All right, for this next one, it says 2 times our vector u minus 3 times our vector v. And so I'm going to do 2 times our vector u minus 3 times our vector v. And so before we subtracted these, you would want to distribute. So I'm doubling this vector, so that's going to be 2 and 4. And I'm tripling this other one, so I'm going to get 9 and 3. Now, just like with this one, now we can combine our like terms. And so I would get 2 minus 9. And then 4 minus 3. You're subtracting both of those like terms, so you want to do that to both of them. And so that gives us -7 and 1. There's the new vector created by multiplying u times 2 and v times 3. All right, we're going to do that same thing geometrically. So they gave us 2 vectors on our graph here. We have vector v and vector w. So the first thing I'm going to do is write the component form for each one of those. So my v vector went to the right 1, 2, 3 and up 1, 2, 3. So its component form would be 3, 3. That's to the right, and that is up. For our w vector, it went to the right 1, 2, 3, 4, 5, 6 and down 1. So there's its direction. This is right. And that is down since it's negative. So if you were going to do it solely geometrically, you don't need that, but I'm going to show you both ways as we go through this, just so you see where that's coming from. So this is vector v and this is vector w. And the first thing we want to do is draw v plus w. So I start with my v here. So I've got a point at 1, 1 and a point at 4, 4. There's v. We are adding w to this vector. That's what we're doing here, v plus w. So I take v and I'm going to add w to it. And so w went to the right 6 and down 1. So I've just added vector w to it. Now, when we get V plus W, I just did that here. So this would be our V plus W. If I'm doing this geometrically, then I want to look from my initial point to my ending point here and see its direction. So it has gone to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 1, 2. So there it is geometrically. I'm going to go back and show you algebraically so you see you get the same exact answer. So for V plus W, we take V and we're going to add W to it. And so we get 3 plus 6, which is 9. And I'll go ahead and write it out so you can see that. 3 plus 6, and then 3 plus -1. And so that gives us 9, and that gives us 2, which is exactly what we got geometrically. All right. For our next one here, we've got draw V minus W. It does make it a little bit easier if it's addition. So I'm going to go ahead and find -W so we can use that one. And so that would make that 6 -6, and it would make that -1 +1. So I start with my V vector. There's vector V. And now we're going to attach our W vector, which we find is -6, 1. Since it's negative, it's going to go to the left. So I go 1, 2, 3, 4, 5, 6. And then I'm going to go up 1. So this right here is our -W vector. When we put those two together, this is the final product. And so that has gone to the left 1, 2, 3, and up 1, 2, 3, 4. So to show left -3, and then to show up 4. So that's how you do that geometrically. It is a little bit harder to do geometrically with the 2 in the front, but we'll show you that. So the initial one was at 1, 1, and 4, 4. So this is just V by itself, but we need 2 times V. So we need to double this. So it went to the right 3 and up 3. So I'm going to go to the right 3 and up 3 again for the double. So there is our new 2V. And then we're going to subtract W from there. So we're going to do this one right here. So I go to the left 6 and then up 1. So there's our -W. And then our final is this last one. That's what we're looking for. That's the 2V minus W. So my initial was right here. It did not move to the left or the right. So that means that's going to be 0. There was no movement to the left or right horizontally. It did go up 1, 2, 3, 4, 5, 6, 7. And so there is our component form. Again, if you wanted to do it algebraically, you would do 2 times the 3, 3 minus our W, which is 6, -1. And so we would multiply that and we get 6, 6 minus 6, -1. And then we combine our like terms. So we get 6 minus 6, which is 0. And then 6 minus a -1, which is 7. So you end up getting the same thing, regardless of which form you use. So on the quiz or test, you could just do whichever one you wanted when it said find U plus V or V plus W. You can do algebraic or geometric. All right, next time we'll do day 2 of vectors and we'll do some word problems with it.